Hi, everybody. This is Dan Conley with Mark Miller and Company. We're here at office hours, and especially today we get to talk about some foundational stuff from the Agoric architecture, in particular, Mark's thesis, robust composition, about access control and currency control. Mark is at slightly diminished capacity due to weather and such in California, so advance notice in case something weird happens with his connectivity. Let's see. There was another discussion I heard about where folks asked you a little bit about history, Mark. I don't know how much of that is useful in this setting. Thomas or Patrick, any interest in the historical context?
Definitely a lot of interest.
Yeah, I'm certainly be very happy to talk about the history. I care a lot about the history.
Well, now's the time.
Yeah, I know.
Well, I mean, it's so okay. So just the general history is that there was a golden age of operating system architecture pretty much through the 1970s. And let's say the late 60s and 1970s. The most famous research operating system, Multics, happened around that time. The object capability, well, at the time was called the capability. Our first capability operating system proposal was 1965 by Dennison Van Horn. That was implemented approximately as laid out in the paper in 1969 on the PDP-1 called the supervisor. And there was, and KeyKOS was born in, KeyKOS, which is really the one that I learned the most from and that most inspired the perspectives that Dean and I have. That was started as Gnosis in 1973. Gnosis standing for Great New Operating System in the Sky. The three main architects of that, which was Norm Hardy, Bill France, and Charlie Landau. Charlie Landau had also worked on the PDP-1 supervisor. All of this happened well before I came into the picture. I saw a computer for the first time in '75. The Agoric Open Systems papers, the papers that our company, of course, is named after, those were, Eric Drexler and I started working on those in '83, and those were published in '88. In that, we lay out a vision of what we would today call cryptographic, decentralized, permissionless, worldwide commerce. And it was assuming that the world was about to build a distributed cryptographic capability actor language based fabric, because those ideas were out there, and of course they made the most sense. That was when I was still a sort of technological optimist that just believed that whatever made the most sense is what the world would clearly then do next. And it was those papers that caused us to be that Norm Hardy, chief architect of KeyKOS, found the papers, saw us state what we saw as the requirements for a foundation for building that kind of system, and that we stated, as was true, that that we knew of no system that met all those requirements, and we didn't even know if those requirements could be met simultaneously. So Norm called us up, said, "We've built a system," he was referring to KeyKOS, "that solves all the problems simultaneously." We met him over lunch, and he convinced us that, yeah, actually, KeyKOS was a beautiful architecture that met all of those requirements simultaneously. So, so that really influenced how Dean and I were thinking about building out this decentralized cryptographic actor language-based architectures for doing this stuff. Norm Hardy then started working with us, and in the mid-90s, we formed a startup named Agorics with an S on the end. And we started working on Agoric systems, market-based, distributed language-based cryptographic computational systems for Sun Labs and for electric communities. For electric communities, we designed the Joule language, which they were using to build electric communities habitats, which was a decentralized graphical social virtual reality system. And due to a contract dispute with the management of Agorics at the time, suddenly electric communities, having built up all of these ideas and plans around the Joule language architecture for how they were going to build their world, where Agorics was providing the Joule language support. Due to the contract dispute, the electric communities was then left without the language support from Agorics. Joule was open source, but electric communities did not want to go into the language business themselves. So that's when a really miraculous event happened, which was up till then, this is on the concurrency control side, up till this point, there were basically two dominant approaches to concurrency that we were aware of. There was the multi-threaded approach, shared memory multi-threading with locks that brilliant people like Tony Hoare and Edgar Dijkstra had done tremendous work creating those systems from 85 through 88. I was at Xerox PARC together with Dean. Dean was already there when I joined in 88. I don't know when he started. But at Xerox PARC, both of these families of concurrency were represented. There was the Cedar language, which is also shared memory, fine-grained multi-threading that had many brilliant people working on them. And the other kind of concurrency architecture we were aware of was the fine-grained architecture like actors that Joule then later was very much in the tradition of. Fine-grained actors and also concurrent logic programming. Flat concurrent Prolog was the particular language that was most inspiring us. At Xerox PARC, we put together a language called Vulkan, which was logical actors, mixing logic programming and actor computation. And that was the ancestor of the Joule project that Dean was the main architect of. And the thing about the dichotomy between those languages is that The actor languages and the concurrent logic programming languages started off without sequential programming. It said, forget sequential computation, start off with an inherently fine-grained concurrent world and build all of that up from there. And then sequence is just a special case of concurrency. And those languages were beautiful. And in the Joule language, we mixed all of those with all of our ideas about decentralized capability computation for security as well. And we had a big adoption and explanation problem with those languages because, of course, almost everybody first learns to program in a sequential language. And what you're asking them to do in switching to a fine-grained concurrent language is to basically learn to program from scratch all over again. You basically can take very little of what you already know into the new world. And we thought we were kind of stuck with this dichotomy because if you start from sequential, the way we were thinking is, well, if you start from sequential programming and add concurrency, then even brilliant people like Tony Horn, Edgar Dijkstra, and all the people in the Cedar group, you end up with the mess that every one of these shared memory fine-grained, shared memory multi-threading with fine-grained locking. Every one of those languages, despite all this brilliant effort, was just terrible. It was a terrible concurrency experience. Nobody knew how to program these things reliably. So we felt like we had to start over by giving up on sequentiality to get to good concurrency. Then electric communities, once they had appreciated all of the virtues of Joule, but were then left without the Joule support, were kind of stuck because they knew they needed what was good about Joule. So Doug Barnes at Electric Communities closed himself, locked his office door, closed his office door for 2 weeks, and wrote a preprocessor for the language that at the time, of course, was called E, but which we now refer to as original E. But that was the first embodiment of the E ideas. And that was basically taking the concurrency constructs from Joule and just adding them on top of the sequential subset of Java. And it worked. And it was beautiful. And it completely falsified the hypothesis that we all had, which is that in order to get to good concurrency, you have to give up on sequentiality. That turned out to just be completely wrong. The issue was not whether you started with sequentiality. The issue was only what concurrency paradigm you're adding to the sequentiality to get concurrency. And shared memory multi-threading was and remains, I would say, nobody has made that paradigm work, remains a disaster with regard to reliable programming. But original E was the first language that had a sequential base, the sequential subset of Java, added the actor style message passing on top of that, and did it with local capability security using language bases, and with distributed cryptographic capability with the CAP-TP protocol, the Capability Transport Protocol, which has since become a family of protocols that we're still using essentially that same protocol design today for doing the language-friendly distributed cryptographic capabilities with actor-style promise-based message passing with promise pipelining. A year later, due to a different contract dispute, this time between myself and the management of Agorics, I then left Agorics and ended up joining Electric Communities, took over being the main architect of the original E language together with Dan Bornstein. And after a bunch of experience with original E, I then realized there was a possibility of a much, much simpler language that's not a superset of Java, but just a from scratch language in its own right, that's still a curly bracket language, curly bracket language in kind of the C syntactic tradition with, that is true to sort of the C programmer's understanding of sequentiality, but that brings in capability-based objects. And so I got very excited about all this and created that language, originally called EZ. Then Electric Communities changed direction. This was later, sort of mid to late 90s, 97, 98. Electric Communities changed direction. They gave up on doing any further work on the original E or EZ languages. I begged them to open source EZ, and the board agreed. It was the sort of the second miracle from my own personal perspective. Excuse me. And also we agreed that we had gotten some uptake of the name E. The board was not willing for the normal short-sighted reasons to open source the language, the original E language, which was at the time called E. So I convinced them to let me rename EZ to E, and to in all of our discussions going forward, for all of us to refer to what was then the E language as originally. That was the renaming, and thus the E language was born. And so I left Electric Communities to turn E into an open source project and an open source community that was formed the erights.org website, which I see somebody is projecting. And that was quite a vibrant open source community where we were brought in many other interested people from across the internet, and we had great discussions. And the archived E-lang and cap-talk mailing lists still remain a great treasure trove of great formative discussions. And so retracing a bit, the Agoric papers were before we had met Nick Szabo, but in retrospect, you would also say that the Agoric papers, the economic level of those, was basically an in-depth exploration of many smart contracts. They were the first significant papers on smart contracting, showing various language-based smart contracting ideas. And the purpose of the smart contracting there was computational resources, memory space, processor time, network bandwidth, to apply the invisible hand to the decentralized allocation decisions of computational resources. Then in the early 90s, maybe very late 80s, I'm not sure, but at least in the early 90s, we met Nick Szabo. There was also the work on Amex, the American Information Exchange, which was the first smart contracting system where computer smart contracts were used to intermediate between people. So smart contracting just grew and grew and grew in importance in our head. The work with Sun Labs that Agorics was doing smart contracts on top of our distributed capability infrastructure. So then when I left Electric Communities to form erights.org, the community around E. E is a general purpose distributed cryptographic actor-based programming language but even though it's a general purpose security, the motivating application from the beginning was smart contracting. And we really started exploring how to express smart contracts well in a programming language. And we did great work. And my first paper on that was published in the year 2000, which was capability-based financial instruments. And that paper, I'll say, holds up very, very well today. And I expected, and that got some very nice attention within the cypherpunk, the crypto finance communities. I was presented at Financial Cryptography 2000 on Anguilla. This was export controls had ended in 1998. So all of the cypherpunk energy suddenly became very open and could be pursued in a mainstream way. And there was this brief window between the ending of export controls in 1998 and the Patriot Act that came in response to 9/11 in 2001. This brief window of like 3 years where all of the cypherpunk energy, we were all, openly dreaming of simply technically building out and going forward this world that we've been imagining without impediment, without not necessarily having any government resistance, since there wasn't any during that 3-year window. And then after 9/11, the Patriot Act happened, and the government got very aggressive at shutting down anything that that they felt smelled suspicious of anything without much due process or constitutional constraints. There was the head of eGold was convicted of enabling money laundering, which was a completely ridiculous charge. There's nothing, there was no anonymity in eGold. Everything was tracked. They were actually working to help report anything that was, it was just a completely ridiculous charge. But under the Patriot Act and after 9/11, they ended up going after him and convicting him. And all of this cypherpunk work went underground. We all continued working on it as we had before the export controls were lifted, but finding ways to do it without necessarily being obvious that that's what we were doing. So in any case, my paper comes out in 2000, and in promoting the ideas in the academic literature, I really become quite aware of the degree to which capabilities as a paradigm had come to be dismissed in academia, dismissed by the computer security theorists. It was viewed as a failed paradigm. And I knew that I had been aware of this conflict through the 1990s, and it just was so obvious to me that the capabilities were on the right foot, and all of our work did so much in the capability paradigm, did so much to build great systems and verify for us that capabilities were the right approach. And our experiences with ACLs were quite awful with the dominant security paradigm, access control lists, or more generally identity-based access control. Norm had already written his famous Confused Deputy paper, laying out kind of a fundamental, irreducible problem with the whole paradigm, the whole identity-based paradigm. But um,
So I
but
have a question. I don't mean to butt in. I just have a
yeah,
question.
please go ahead. I went into lecture mode and I did not
No,
intend
no,
to. Go ahead.
that was fantastic. Thank you for everything. So this is just kind of coming back to your early work. Like so it's really amazing to learn that it was in 1975 when you touched your first computer. And then by the mid 80s, you were already able to envision really the future that we're trying to build today. And more importantly, building this out securely. So I'm wondering, so do you think that it was like KeyKOS, or what do you attribute like your ability to kind of view the world through this lens uh differently than kind of how software, like the software engineering this sector kind of progressed since that time towards using access control lists? And just because as somebody who began programming 10 plus years or so ago, there's so much information out there, and I think access control lists have just become the default, and capabilities is so not widely known, which is so surprising when you see the clear benefits. And so, yeah, I kind of have a loaded question there, but the first part was, yeah, what do you attribute just kind of being like, how are you able to envision, like, predict the future?
Okay, great. I love this question. There's several key elements that were quite formative in my uh, uh, being able to see forward in these ways. One thing is really very generic, but I think should not be underestimated in its importance, which is I was a big reader of science fiction that and taking very seriously from having been exposed to so much science fiction that technological progress shapes the future more so than anything else, which I still believe, and that it can take the future in surprising directions, and that the future can be very, very different than the present, and it can happen fast. So just sort of generally approaching all these matters with that seriousness about technology and progress and change of the future. In 1975, a friend of mine handed me Ted Nelson's book, Computer Lib Dream Machines, which was Ted Nelson, a really great visionary, his dreams about the future of computing, which was largely focused on the future of interactive systems. But it wasn't a shallow focus on the screen. It was a really quite a deep focus, driven by the notion of people interacting with information on computer screens. But he was one of the two great hypertext visionaries. Very brief history of hypertext, just sort of biased towards highlighting how it influences the main story I'm telling today. Hypertext itself started, in some sense, with Vannevar Bush's 1945 paper, As We May Think. Vannevar Bush was President Eisenhower's science advisor. He published an article in The Atlantic imagining what we would now call a user experience of hypertext documents, of linked documents, but he was imagining it all. He was painting the picture as the future with microfilm and microfiche technology, because that's all that they had to imagine it with. Doug Engelbart and Ted Nelson both remember reading that article as children. They grew up in the 60s to form the two great hypertext visions. Doug Engelbart, the augment system, NLS, which, by the way, all of the KeyKOS design documents were done in augment. And a lot of the beauty of KeyKOS is they attribute to what was some of what was different in the design process that was possible to them because they were writing their documents in augment. And then also Ted Nelson in the early 60s formed the Xanadu vision and started building that out, and then really explained it very, very well in Computer Lib Dream Machines. When I read Computer Lib Dream Machines, I was really grabbed by the whole Xanadu vision, and ended up deciding that that this whole vision of computation from that's laid out here was very much the computation that I wanted to learn about. So I ended up in the summers between school. During the summers, I apprenticed myself for free to Ted Nelson. I contacted Ted Nelson, but apprenticed myself to him. I ended up working on the Xanadu project, becoming the chief architect of what became known as the Xanadu Green architecture. But at Xanadu, part of Ted's vision was, and this is why the book is called Computer Lib, is computers and decentralized networks and worldwide hypertext publishing as a liberating force. We were, both Ted and I were quite terrified of the vision laid out by George Orwell in 1984, but being Ted's apprentice, I very much absorbed this notion of the future is a choice. We can either end up in a world of 1984 style oppression, or we can end up in this world of hypertext publishing, of electronic publishing on computer networks, if we can figure out how to build those things out in a way that was free of censorship, free of modifying of history, which was one of the main forms of oppression from 1984, and free of monitoring, something that was inherently private. One of the things that was an essential part of the Xanadu vision and then of the Xanadu architecture was for nobody to be able to know what you're reading. That's the thing that I found most bizarre about the hypertext system that then took over the world, the web, which is with the web architecture, not only can the server that serves the document know what document you're reading, but with the Web 2 architecture, they can know where you are in the document, how much time you're spending looking at which paragraph, how your mouse is moving. The degree of violation of privacy of people reading things to take in information is just something that it's just not in my wildest nightmares would I ever have thought that masses of public would have accepted that kind of loss of privacy. So in any case, I very much absorbed from Ted this notion that we're at a choice point, that humanity is at a choice point, that these electronic networks are coming, and it could be a 1984 style nightmare, or it could be a great liberating force. And I also very much, sort of took up the idea that it was our responsibility to figure out how to build the great liberating force, that how it turns out depends on what we build. And we,
Sorry. I don't want to butt in. Right. Yeah. So I'm just curious, how do you think you said never in your wildest dreams would you have imagined kind of the current state of Web 2? How do you think because you guys had such great visions, right? For building just this private, um, yeah, just infrastructure. Yeah, I'm wondering just where things went awry, or where do you think things went
Yeah.
awry?
So, so part of why it went awry was actually, I'll say, my fault, or primarily my fault, which is in 1989, Dean and I both left Xerox PARC to form the newly funded Xanadu project. Um, uh, uh, Xanadu had been going on unfunded on a shoestring throughout all of this time until 1989, when Autodesk decided to fund it. We then formed this really wonderful startup to build out, to really build the Xanadu hypertext system. And there were two things we got wrong. One was we had a notion of what features you needed simultaneously to have a hypertext system that would create good social emergent effects. There were basically 7 fundamental requirements. And this is laid out in my paper, The Open Society and Its Media is what those 7 fundamental requirements were. And we built a system that did those, but it took us longer than was expected. And we kept having these triage meetings where we tried to figure out if we could drop something in order to get to market faster. And we kept talking ourselves into the fact that, well, if you drop these things, you get social pathologies. So you really need all 7 in order to get the kind of beneficial emergent social effects on the evolution of society's knowledge that we were looking for, that were motivating us. And as a result, the project went long enough that Autodesk, our funder, ran out of patience, well, partially due to a management change at Autodesk. So we were already in beta with the product. It was not in beta. We already had the features working. We were demonstrating we had the features working, all 7 features, but it was quite a long way from really having been something that was a commercially viable system at that time. By the time we ran out of funding. The other thing we got wrong is none of us appreciated what we would now call open source, which was then called free software from because Richard Stallman's way of explaining the virtues of free software didn't make sense to us. And it wasn't until later with the open source movement that we really came to understand the power of it. But the result of those 2 things is that we built something where the technology itself was quite intricate and needed a bunch of work before it could be used commercially. And it was proprietary. So without funding, it was hard to figure out how to continue to advance the system. The web came out with 2.5 of our 7 elements, and took the world and was a simple architecture and was open source, simple enough with text-based protocols, which is still kind of insane. Text-based protocols so that people were able to put together web servers with very, very little software, which itself is quite wonderful that you could do it so simply. But with 2.5 of the 7 elements, it proceeded to have all of the social pathologies that we were worried about. In my paper, The Open Society and Its Media, there's 2 paragraphs in that paper that I would say really explain pretty damn well what we then later came to call filter bubbles and echo chambers and all of those things. So that's how Xanadu died, and it was in the light of the death of Xanadu that Dean and I then left Xanadu and formed with Norm Hardy and others Agorics in the mid-90s, dropping the hypertext part, but taking forward the liberation goals, the software, decentralized cryptographic software systems, but now general purpose computational systems that could support hypertext and other things, could support just general purpose, decentralized, secure, permissionless programming. If you can support that in general, then any particular decentralized application like hypertext, you can, of course, build out of that. So that was one of the formative elements. Another formative element is I had, what was the time frame here? I'd say probably early 80s. I was a really big fan of object-oriented programming and then of actors. And separately, or thinking it was completely separate, I was also becoming very, very interested in economics, and in particular in the writings of an economist, Friedrich Hayek. And I was explaining, I think I would say around 1983, I was explaining to my friend Eric Drexler about the virtues of encapsulation in object-oriented programming, how for every piece of data that it's encapsulated within an object, so that with regard to the there's only a finite amount of code that you have to look at to know whether the invariants are being maintained in the data, that this coupling of encapsulated data together with code. And Eric said, oh, that's like Hayek's explanation of why property rights are important. And that was the big aha experience that brought the thinking about computation and the thinking about economics together in my head, realizing that they were, at an abstract enough level, solving the same sets of problems in the same sets of ways. That the way I would, the way I've been putting it, since then, or more recently, is both large object programs and the human economy as a whole are networks of entities making requests of other entities, and that the nature of the request making is the request contains both an informational component and a rights and incentive component, that there is the transfer of information in the request, but also the transfer of rights. So this really led to, so it was from 83 to 88 that Eric and I worked on the Agoric Open Systems papers published in 88. And that very much caused me to see the foundations of the economic issues just very directly in language-based terms. And that's what led to the appreciation of capabilities, which is capabilities are the rights that are transferred in a request from one sovereign entity to another sovereign entity. And that's, seeing that from the object-oriented perspective and seeing that from the economic perspective, the only kind of economics that you can map to object-oriented computation is one that recognizes the object reference as the right. So it very much led us to a much deeper appreciation of the capability perspective, sort of the only perspective that supports decentralized rights ownership and rights transfer as the foundation of computation.
Very interesting. A lot of aha moments clearly over the last few decades.
Yeah.
So on the topic of property rights, is it just because they're more fine-grained? Or could you maybe elaborate why they fit so well as opposed to like just regular contractual obligations for this system?
So the way we saw it is that the capabilities were a foundational rights theory, and that there were all sorts of other forms of rights and that you needed to build in order to get economic, in order to get economic phenomena, or to build smart contracts and economic institutions. But every time we tried to figure out how to build those, starting from capabilities as the foundation, we ended up happy. And every time we tried to build them on any other foundation, we ended up sad. So it just kept reinforcing from us that capabilities were a great foundational rights theory from which to build out the others. And then once we met Norm and understood the KeyKOS system really took this foundational property rights perspective to computational resources themselves. It was, the first system to really do that in a principled manner. That rights to memory, rights to processor time, all of these things were managed as capability-based rights, and that one of the exercises in the KeyKOS introductory programming class was build a money system that the mint maker that I made famous in the capability-based financial instruments is kind of inspired partially by the KeyKOS meter abstraction for CPU time, and partially by the way in which you build, in which that exercise had you build money out of capabilities as a KeyKOS programming exercise. By the time I got to capability-based financial instruments in 2000, I had this notion that there were a bunch of different dimensions on which rights could differ. Capabilities themselves are rights that are transferred by sharing. When you send the right, the sender still has the right, and the receiver has to assume that the sender still has the right. So there's whether the rights are shared or exclusive, whether the rights are specific or fungible. Specific we took as the base case. So the idea of calling the specific, and the fungible was the weird one that had to be explained. So the idea of of calling the specific non-fungible, taking fungible as the normal case, was just kind of odd. Always seems like odd terminology to me. Symbolic versus exercisable rights generally are something where if you have the right is the right to do something. Money is peculiar in that it's just the right to transfer the right. Is if you holding the right does not enable you to do anything, it just enables you to transfer it. So in any case, so at that point with capability-based financial instruments, we realized that there was this whole taxonomy by which rights could differ, but we were very satisfied that the right foundation for building out the taxonomy was to have capabilities of the foundation and then to do all of the others at higher levels of abstraction. And that remains the case, and that's that's what we're doing. And I should mention that all of this was without blockchain. Blockchain was not part of our thinking. Blockchain, we were not anticipating anything like blockchain. This whole paradigm of decentralized permissionless smart contracts was decentralized in the sense that the web is decentralized, just lots of little sovereign parties interacting with interacting with each other securely through cryptographic protocols. And blockchains, when they did come about, were just kind of bizarre to me. And then when Ethereum came out, I realized that that the blockchain-based smart contracts was actually very much along the lines of a paradigm that Nick Szabo had been trying to explain to me in the 90s, that I just was never able to understand what he was trying to explain to me until I saw Ethereum. But even after that, I then couldn't figure out how to bring together my way of thinking about smart contracts with the smart contracts on Ethereum. I just couldn't figure out how to reconcile those two. And the Ethereum-based smart contracts were then taking off. It was Jorge Lopez who was very much in the blockchain world, but who had also discovered my papers and was reading up on that. And he had figured out, he had come up with his own vision of just how to combine the, what was, our non-blockchain based vision of decentralized smart contracts, how to combine that with blockchain-based smart contracts. He found me, explained to me that combination. And it was really that, more than anything, that led me to realize that there was a commercial opportunity for me to leave Google and form a blockchain-based startup to bring my kind of language-based decentralized smart contracting into this new growing world of blockchain-based smart contracting. And that's what led to the creation of Agoric.
Very amazing. So, I know our time is a little bit short here, but I do just have 2 questions. One about blockchain. So in order for a secure multi-party interaction, like true rich composability to occur, is this going to require that all systems adopt just like an OCAP compliant architecture?
I'm sorry, the audio got garbled there. That all systems adopt, and I couldn't hear the next.
Adopt just OCAP compliant like architecture. Sorry.
So I never want to claim that no other architectural basis is possible. That it's always possible that we discover yet another paradigm that's superior to OCAPs and not built on OCAPs. But OCAPs has been with us from 65 till today, and has remained superior to all of the paradigms that have gotten invented since then. So,
Mark, which part of the thesis talks about reasoning about people far away as just reasoning about objects? I forget how you phrased it.
Yeah, you can reason about all suspicion as if you are suspicious only of objects. So that's a really key thing that was not anticipated in 65 when the capabilities were invented. That was really a realization by Jed Donnelly in the late 70s, I think, realizing that that the capability security notion transparently distributes over a network with this property that the way I explain it now is that if you're suspicious of another machine, but you're interacting with the other machine over a capability-based protocol, then the other machine might be misbehaving. It might be speaking the protocol badly, or it might be running the objects, the capability-based objects let's say you're doing a language-based local capability system on that machine. It might be violating the capability rules at that location. So it might be misbehaving in all sorts of ways. But due to Jed Donnelly's insight, it became clear that if you had the right kind of cryptographic capability protocol, that the total damage to me of a remote misbehaving machine is equivalent to the damage that could be done by a correctly behaving machine, correctly in the sense of speaking the protocol correctly, and correctly in the sense of running its own local object capability language or operating system correctly, equivalent to a correctly functioning machine or platform running a malicious group of objects. That if I'm ignorant of what the actual object graph is that's running on the correct platform, that the dangers to me of that group of malicious objects is equivalent to the dangers to me of the machine that those objects are running on itself being malicious. And as a result, I can model my worries. I can do all of my reasoning about my hazards from suspicion of other things as if it's only object misbehavior that I'm worried about. Now, there's a whole bunch of qualifiers I need to put on that. The main one is that those statements are really specifically about integrity. It's not about confidentiality, and it's not about availability, it's not about resource use. Those things need to be revisited and see how close we can get. But the strong statement is only a statement about integrity. And it's that insight from Jed Donnelly that really led to the nature of the CAPTP protocol family that we're currently building out on.
Yeah, that was kind of what's interesting to me, is that when you look at things through this message passing OCAP lens, you can talk about, objects being suspicious of each other inside the same JavaScript runtime, or across JavaScript runtimes, or across Unix processes, or across machines, or across blockchains, or whatever.
Yeah.
And what I like,
Yeah,
what I like
exactly.
about these properties, what I like so much about the properties too, is that you think of in terms of what damage can be caused to you. Well, the only damage that can be caused to you is somebody sends a message to one of your objects. So if you expose an object to some other object, then they can send a message to yours. And if your object is defensive, then they can't do anything bad with it except for these resource constraints and the other stuff that Mark mentioned.
Right. And so using that, I can explain this equivalence in a fairly direct manner, I think, which is the cryptographic capability protocol says that a misbehaving platform can still only exercise capabilities remote to itself, can only send messages to objects remote to itself that are capabilities that had been granted by a message pass to the machine, to that machine, which meant that somebody thought they were sending a message to some object on the machine. So the worst case risk to a misbehaving machine in terms of what messages it can send, in terms of who it can send messages to, is the union of all capabilities that have been sent to any of the alleged objects on the machine. And if you just have a misbehaving object graph running on a correct platform, then the worst case misbehaving object graph is it's just a big grand conspiracy where they all pool all the capabilities sent to any of the objects, which they then jointly misuse. So that I think that should be a fairly straightforward and intuitive explanation as to why the right protocol makes these two risks equivalent.
Yeah, that was very helpful.
I could do this for many hours, but I do have a 10 o'clock meeting that I should not be more late to.
Right. Okay, well, we'll
Appreciate
think
it.
about whether we should do something like this 1 week or N weeks hence or something like that. It's been interesting listening to all the history and stuff. So I'll let you go, Mark, and then I'll see if anybody else has any questions that I should take care of for other stuff.
Thank you, Mark.
Okay. Yeah, thank you. I love having a being able to discuss this, having having people who are interested in this. So I really appreciate it.
We're deeply interested.
Yes, thanks for your time, Mark.
Thanks for your time, Mark. Appreciate it.
Thank you.
I'm just going to peek at a couple of the. So, did anybody have anything today that we didn't take care of offline or something?
Nothing on my end this time.
Me neither. I noticed that I missed the initial time of the office hours, but I will see the record later.
Right. We did record the whole thing today.
Yeah, thank you.
Oh, one thing, Jorge, I don't know if you have a question. I don't mean to cut in.
No.
Just one thing, Patrick and I were discussing was related to the no nested await. So wondering if you could just take a minute to kind of go over the why you can't use any nested await and just what that might lead to. And also, could this enable reentrancy?
No, it can't enable reentrancy. It's just but it's a hazard. It's a bug farm. Is the way Dean describes it. If some of your code paths split turns and some of the code paths don't split turns, then part of your brain thinks you're not splitting a turn, and so all your invariants staying still, and part of your brain realizes that every time you split turns, you got to recheck your invariants, and the two halves of your brain can not talk to each other. And the empirical evidence is that this is a source of bugs. Now, we have managed to come up with a less drastic rule that we haven't shoved out. I can go, let's see. Okay, so it's sort of like, look at this code and spot the bug. Well, it's really hard. And I'd have to go and read this text and stuff. I don't know if you've managed to actually study this.
I mean, a little bit. A little bit. I mean, if there's a bug in that thunk, right? Is it never going to go to that finally?
So if the thunk throws synchronously, the await is bypassed entirely. Oh, right. If thunk throws synchronously, is that really true? There's no turn here, Michael?
I think he dropped.
Oh, okay. Well, You have to know more than I do. I think if this throws synchronously, then this await doesn't even cause a turn break. So it can go straight to here. Let's see. This is made by more obvious by doing a supposed promise.
Is a turn the same as a crank?
No.
Okay.
I can elaborate on that. If that I know for certain, I can tell
Yeah.
you.
Yeah, because I was looking at the atomic versus transactional state. And yeah, I was reading concurrency among strangers as well.
Mhm.
And I think I kind of understand, like, if the objects are in the same vat, and a contract could be considered a vat, then it's synchronous.
Mhm.
But if you have to reach out to a different contract and rely on that result, then you're potentially introducing an interleaving hazard, and you would just need to recheck all of your invariants.
Right. Well, even async
and those-
calls within a contract, or you need to check your invariants again. Because you make a call, that puts something on the queue, then some other message from another vat comes in and gets to run for a while, then your code resumes. Right.
Okay.
Or even just your own code doing weird things.
So,
Anyways, go ahead.
okay, yeah. So then, yeah, if you could explain a turn and a crank, and then I'm also trying to understand how this fits into a blockchain transaction. Like, what's the boundary there?
Maybe a quick question. Does this stuff apply to JavaScript in general, or is it specific to Agoric?
Turns are JavaScript in general. Cranks and blockchain blocks are specific to Agoric.
Yeah, sorry, I meant more the nested awaits, or like the pattern.
The no nested await
That-
is a JavaScript recommendation.
Yeah, okay, thought so.
That's not the file I want. Where's the one that talks about cranks and stuff? Darn it.
Is it comp? Is this comms or
I would be surprised if it's comms, but
make reds? Okay.
nope. Come on.
Few more guesses.
Yeah. I thought it was state. Hold on just a sec. Just a moment. Delivery. Oh, there we go. It is state. Right. Okay. So a turn is from one empty stack to the next. Let's see. We define a turn as a span of computation from one empty call stack to the next. So, in general, you're doing a event loop, and so some event comes in and calls some function, right? And then that function calls another function and calls another function or whatever, and then pop, 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 and then you're done with that event from the event queue, right? That was a turn.
Yes.
Okay,
Yep.
and that's in web browsers have those, and Node.js have those, and everything like that.
Mhm.
And then a crank is one empty promise queue to the next. So while you're doing one turn, you can queue up more promises, right?
Yes.
Yes.
Right. So, the first turn queues up a promise, and then the second turn queues up a promise, and then the third turn doesn't queue up a promise. So then your promise queue empties, and then your crank is done.
Okay.
And so
Okay.
the way swing set does things is when it delivers a message to a vat, it lets the vat run for a whole crank, unless it exhausts a meter or something.
Okay,
And
cool.
then
And that-
go ahead.
And that promise queue can contain like eventual sends as well.
Yeah.
Okay.
I mean, every eventual send spawns a promise, right?
Okay.
Some eventual sends go to your own vat, some eventual sends go to another vat. At the end of your crank, there's going to be 0 or more outgoing messages, right?
Yes.
And so none of those get delivered until the whole crank commits. So, okay, anyway, then a block is a group of cranks. So, you know, it'll be some number of cranks and all of them are, you know, like transactional. So either if you got the 10 cranks, you're not doing 9.5. You do 10 whole cranks and then you call that a block.
Okay.
And there's some policy about, you know, how many cranks to fit into a block. It's based on computrons right now, but we kind of experience shows we're trying to do better than that because they end up really lumpy.
And then like, given how like, you know, Ethereum and most blockchains every transaction is initiated by a user. In Agoric, we can have, you know, notifiers and other sorts of things initiating events. How does that get communicated on a blockchain if there's like some sort of state change? That still goes in as like a normal transaction and maybe the author's like the contract or something. What does that look like?
Let's see what does that look like. The author of that message is the kernel. There's a kernel device that's a timer, and there's a timer vat, and the timer vat is like any other vat. It's sitting there waiting for somebody to tell it to do something, and then the timer vat basically tells the kernel, hey, nobody is interested in anything happening until 5 p.m. tonight. And then at 5 p.m. the kernel goes, hey, wake up. It sends it a message, just like anybody else sending it a message. And the timer vat wakes up and says, oh yeah, Bob wanted to know that it's 5 p.m. And so it sends a message to Bob. So there's not a signed transaction from anybody at that point. It's just the kernel in the course of running a block notices that it's 5 p.m. And so it sends a message to the timer vat.
Okay, cool.
Yeah, that is somewhat novel. So the other thing to think about is if you're contrasting this with other blockchains, is most other blockchains, you send a message to the blockchain and it does a bunch of computations within one block and it's all done and you get the result of your computation, right? Whereas in Agoric, you send in a message and what happens, the transactional thing is your message gets queued in the swing set queue. And when it actually runs and completes and gives you information back, maybe weeks or months or years later. So you don't really know the result of your your quote transaction until later. So it's if you're doing something you thought was just one thing, like I just want to buy, want to do one PSM transaction, you're saying, what? I have to wait 5 blocks? Well, maybe. So
yeah. I know there's a Kate Sills article where she says, you can have a transaction that spans multiple blocks, and that was kind of hard to wrap my head around, but pretty cool.
Right. Well, it's not really the case that there's transactions that span multiple blocks. It's that we don't really have transactions in the way that, I mean, basically what we have is cranks. So you send a message in and then your crank might happen in this block or some later block. And that crank may spawn more blocks and, or more cranks, and they may happen later. So you're sort of starting some computation.
Is there any way as a developer to control like the cranks, or would there be any need to want to control that? Like, hey, I want my transaction to only span one block, or I want this to span multiple blocks.
Well, what do you mean by transaction?
Sorry, I shouldn't use the word transaction.
Yeah. So
my cranks. I want, like, should we be thinking about how we control the cranks and batching them together? There's one PR linked from Dean where I think it's old and this design is not around anymore, but I lost the tab. It was for an auction and he had some generator that made sure it only fired once a block.
Yeah, that's about as good as you can do because you can sort of use the timer. You can say, wake me up 0 seconds later. And the minimum it can wake you up is the next block. I think is what he was using there. So the main thing mostly you can just be unaware of cranks. If you wanted to be aware of cranks, we don't expose that to you. That would be kind of a non-determinism problem. The thing to be concerned about is that you don't do too much computation within one crank because we could shoot you. So if you get into an endless loop, you lose.
Yeah.
And we're not doing metering now, but we plan to do metering, so you could run out of money, if your crank runs too long. And there's discussion about whether you get shot or whether you just get frozen, and so until somebody sends you more money and you wake up or whatever.
Okay, cool.
We used to have the metering stuff, and then we postponed it.
Yeah, I suspect that that's really the level of thinking we'll have to do though about cranks and turns. Will mainly just revolve around using metering effectively, efficiently.
Right. So in mainnet 1, only Agoric gets to write code that goes on the blockchain. So we're not going to, we just make sure our contracts don't go crazy. So there's no need for metering, right? Mainnet 2, it's kind of like, well, it can be some party other than Agoric authoring the contract, but we're going to review it carefully enough to be persuaded that it's not going to go crazy. So maybe we still don't need metering. And then mainnet 3, it's anybody's game. And so then you need metering because, day one, somebody can write an endless loop and then your blockchain goes blammo. So remove proof of concept Zoe metering. There it is.
Yeah.
So did I miss a memo?
Yeah, that was abrupt, right?
No, look, there's the design rationale.
No, I know, but it was just you seemed to be you were surprised.
Yeah.
It's a quick, but it makes sense. This is
And then Dan, maybe building off the crank stuff a little more. How can we think about like rolling back partial state updates? So say, down the road, there's a bunch of DeFi protocols on Agoric. I'm an arbitrager and, I do a bunch of actions, but then at the end, I do a check to see if my profit is greater than 0. And if it's not, I roll everything back. We kind of have like in Ethereum, that's pretty easy to do. But how should we be thinking about that in Agoric, since you can, it would seem, have like parts of state updated in between?
Yep, can't do it. Once the crank's committed, it's committed.
Okay.
Yeah, there's no flash loans and no undo.
Yeah, we could, but we'll just, as long as offers aren't fulfilled, right? I'm just thinking about it.
Right, if you don't exit the offer, yeah. I mean, you can sort of, in your contract, you can futz with things and then decide how you want to exit the offer. You can say, oh no, let's put all the allocations back before we exit the offer.
Yeah. So it's not, I don't think it's like a limitation, it's just having to think about it differently.
Yeah, I guess
Yeah,
you can look at the Zoe offers as a corresponding unit. The flash loan thing is just no way. So that's just, Ethereum has it, we don't.
Hmm. I get
Like
it.
just flash loans generally aren't possible.
That's right.
Why?
It's
Why?
because of our approach to reentrancies, because everything between between VATs is asynchronous, and so flash loans are synchronous by nature.
Ooh, I'm not sure if I'm following what flash loans being synchronous by nature. Like they almost behave asynchronously. I would like when I kind of view the way I view them.
No, they're completely within one transaction, within one block, right? They're all sequential compute. There's nothing async about a flash loan.
Yeah. So on Ethereum, yeah, on the EVM, yes. But I don't have an answer right now. I'm just thinking, if I'm not going to use a good example, you just had a series of steps like take this flash loan, exchange these do a swap on osmosis for the, or let's not use osmosis, but do a swap on a native Agoric DEX, and you can kind of execute a set of instructions asynchronously, and at the end, if the offer is fulfilled properly,
Yeah, you
Yeah.
could probably roll everything back, but you might incur some slippage or something. Like if you swap the tokens and then you miss the liquidation.
So you can do all kinds of thinking about moving assets around within a smart contract, but not actually moving any assets around. If you want to actually move any assets around, then there's no undo.
but the assets aren't moved until reallocate, right? So
Within a contract, right? But if you go from your contract to the AMM, and you put up some assets to in the AMM, you've moved the assets. That's not just thinking about moving them.
Mhm.
Although you could make it, no, once you've made an offer, the assets get escrowed in Zoe. You might be able to, there is an exit. You can exit an offer, but you're sort of racing against the clock. If the transaction goes through before your exit goes through, well, the thing about a flash loan is you borrow a bunch of money, and then if you don't pay it back, oh well, the transaction aborts and it rolls back, right?
yes.
Right.
So say you had one contract that had loans and like liquidations, and then there was also a DEX. So like kind of one, and this had the liquidity to support a flash loan. That could potentially work, right? If it was all within one contract or protocol.
Yeah, I would hesitate to call that a flash loan. I don't know. You could have a contract where
Like just assuming all the state was synchronously available, you could check all the invariants and then do the commitment from there.
yeah.
How would you have it synchronous though?
He's just assuming, I think you're just making
Well, I just said synchronous because if you have, a VAT not having to reach out, VAT or a contract not having to reach out to other contracts across VATs, if everything is in there, then I think that's when it's synchronous in Agoric, and
that's in general how our system works. It's like, I want to get a hotel and an airline and a flight. You have to get a reservation for both resources, and you have to sort of escrow all the resources in one VAT, and then do the transaction atomically, which you can only do synchronously, right? So you have to gather everything into one vat in order to do the commit, and then you can go back and talk to the rest of the world. So it's like if the if you want to do some transaction across 3 blockchains, you have to sort of what's it called? Not burn, but you kind of have to sequester the funds so that you can escrow them in one place and then do the transaction and then go back and tell people, yep, it's done. It's kind of two-phase commit thing.
Okay.
I mean, the Agoric blockchain is sort of like assumes that everything happens over IBC, right? You can't have a flash load over IBC.
There actually is, so that last thing you just said, Zucky shared with us something he wrote called Cinderella tokens, where, yeah, basically a bunch of assets get escrowed into a contract and there's a timer, kind of like Cinderella or
Oh, right.
turning into a pumpkin or whatever. So then, if whatever the invariants aren't met, then the
Interesting.
wrapper token kind of expires. But yeah, I guess that kind of co-locates everything into one vat for a period of time.
So you can have like a dead man switch. Yeah. I've heard kind of, there's arguments on both sides. Some people have said flash loans are a bad thing, but other people have said, hey, look, there's all kinds of uses for them. And I've heard somebody say that you can't do a flash loan in the real world. A flash loan is like locking up all the banks in the world and saying, hang on, I get to use the whole world's financial system for a minute here.
Yeah, I think that there's an argument for constraints, right? There's an argument for open systems where you could perform whatever logic you want to program, but yeah, I think it's fair to say that it doesn't need to be like
Unbound. Yeah.
Mhm.
So that would be an interesting one to stick in the discussions.
Here, I can send you the gist. I'll pop it in
Yeah.
the chat here.
Oh, there's 6. I always forget about Zoom chat.
Oh, good. I'll share. Thanks.
No problem, Patrick.
Daylight savings time.
Yeah.
Yeah, totally missed it.
Yeah, there was somebody said, happy time zone confusion fortnight to those of you who celebrate.
Yeah, pretty much.
Anyway,
I grew up for like 8 years in between time zones where we didn't change our clocks, and then when I moved and we changed clocks, I still haven't gotten adjusted to it.
it's really great. I don't know why we don't do away with it. I guess we just can't muster the political will to get rid of it.
I thought they were. It's off topic, but I thought it was like the last year of it or something. But
There are a lot of talks of doing it in Europe, but I don't think it went through in the end.
Yeah. Who knows what? There's too many implications. So the world will stop. Yeah. I'm joking.
Yeah.
Yeah, can you make sure that Agoric swing set state document ends up in the notes too? I forgot to grab the link.
Yeah, let's see.
Frank and stuff.
I sent it to you too, Pat.
Thank you.
Where did I put it? It's probably in here, but I can double check.
The tab dump today is going to be super valuable.
Well, let's do it right now, and we can double check. Here, I'll share screen again. Oops. So this tab dump thing, I love it. Copy 24 tabs. Is it in there? It's not, is it? I must have reused a window.
Swing set docs.
There it is. Now it's in there. I may double check that I didn't reuse other things here, stick them in there.
Yeah, if I notice anything too, I'll reach out.
All right. Move this thing over.
On the Ides of March.
Hmm. Whoosh.
All right, thanks.
Nope, put that one. All right, I should scoot. Thanks, everybody.
And thanks, everyone.
Thank you.
Thank you.
Thanks. See you all next week.